In this video, we start considering reversible carbonyl addition reactions and the ramifications of what that means. Okay, so in the last video, we reviewed the addition of sodium borohydride to aldehydes and ketones, and we said that that reaction is irreversible because a very strong base, namely H-, is replaced by a much weaker base, RO-, in the key step of the mechanism. The reactions that we will discuss in this unit, however, are reversible. This means that the products and starting materials, first of all, have similar energies, which in chemistry speak, we say that delta G for the reaction is close to zero. Okay, what do I mean by close to? Well, close to zero in my book means less than plus or minus 3 kilocalories per mole or 12 kilojoules per mole if you prefer. So based on the equation delta G equals minus RT ln K, which is a standard equation of general chemistry, you can calculate, plugging in R and T, if delta G is negative 2.8 kilocalories per mole, the reaction proceeds 99% of the way to completion. Secondly, for a reaction to be reversible, the reaction must have a reasonable mechanism for both the forward and backward directions. In other words, no step in the mechanism has too large of an activation energy. The reason why the hydride addition is an irreversible reaction is if you tried to go backwards, you would have to kick out H- as a leaving group, and H- is of course way too strong of a base to be a reasonable leaving group. So when we talk about reversible reactions, we now have to consider the possibility of equilibrium. And in order to do that, we need to review a little bit about equilibrium. So the first thing I want to review for you is that when a reaction reaches equilibrium, it has not actually stopped. The reaction for a particular molecule is still taking place, both in the forward direction and in the backward direction. But what it means to have reached equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. They're both taking place. Some molecules are going forward, some molecules are going backwards, but overall, looking at the entire reaction, the forward reaction and the backwards reaction are taking place at the same rate. Therefore, the amount of reactant and product will not change anymore over time. Okay, so for a generic reaction, A plus B in equilibrium with C plus D, where we call A plus B the reactants and C plus D the products, K, the equilibrium constant, is equal to the concentration of the products, C times D, divided by the concentration of the reactants, A times B. So the nucleophilic substitution reaction that you have already considered is often a reversible reaction. So if you consider the reaction of ethyl bromide with sodium iodide giving ethyl iodide plus sodium bromide, this reaction is actually a reversible reaction. The equilibrium constant, all else being equal, would be close to 1 because the driving force behind many nucleophilic substitution reactions is converting a stronger base that is present in starting materials to a weaker base as the leaving group that has been expelled in the product. But in this case, the bases that you need to compare are I- and Br-. Those are both very weak bases, and they are similar in strength. So therefore, intrinsically, the equilibrium constant for this reaction is close to 1. So how do you drive an equilibrium to give a good yield of desired product? Well, I want to again stop for a minute and say, what do I mean by a good yield and desired product? Well, as organic chemists, me as an organic chemistry teacher and you as organic chemistry students, What we care the most about is the organic product. We don't care how much we have of inorganic byproducts or inorganic starting materials. Specifically, if a reaction is done, the ratio of ethyl iodide to ethyl bromide needs to be large. So to make that happen, looking back at the equilibrium expression, what we can do is take advantage of Le Chatelier's principle. And the term I like to use for this is we Le Chatelier the reaction to completion. So what does that mean? What does Le Chatelier's principle tell you? It says when a stress or strain is placed on an equilibrium, the equilibrium will shift to mitigate the effect of that strain. Well, that's gobbledygook to many of you. The practical application is if you are trying to convert A into C, if you use more B, inorganic starting material, and or remove D, the inorganic byproduct, that can drive the equilibrium towards products. So in this reaction, if we use an excess of sodium iodide and remove sodium bromide, sodium iodide being reagent B and sodium bromide being product D, we drive the equilibrium. And for this particular reaction, it actually happens in practice. Removal of sodium bromide from solution, okay, equilibrium just applies to what is in solution. Removal of sodium bromide from solution is easy if the reaction is carried out in acetone as a solvent. Because sodium bromide is insoluble in acetone, and therefore as soon as it is formed, it precipitates out of solution. Sodium iodide is soluble in acetone, and therefore it is present in solution. Adding more sodium iodide, an excess of that reagent, increases its concentration in solution to further drive the equilibrium. Okay, so that is an example of how driving a reaction, Le Chateliering a reaction to completion, is practically carried out on a reaction that you are familiar with. So as we move forward through this unit, for every equilibrium reaction that we consider, we must consider what steps we are taking to ensure that that reaction goes to completion. And for the different reactions that we'll be looking at in this unit, the answer is going to be a little different. We will start our tour of carbonyl addition reactions in the next video when we begin to consider the reaction of oxygen nucleophiles with carbonyl groups.